Hello, and welcome to today's panel on machine learning for robot manipulation and dexterity. My name is Kevin Lynch, and I'm the editor-in-chief of the IEEE Transactions on Robotics and director of the Center for Robotics and Biosystems at Northwestern University. This is the fifth and final panel in our series on the grand challenge of robotic dexterity. The purpose of this series has been to bring together thought leaders in robotic manipulation and to engage the broader community on topics such as the challenges to achieving advanced dexterity, high-impact applications of robotic dexterity, and the potential economic and social impact of easier-to-program, more dexterous robots. This series has been motivated by the recognition that progress in robotic dexterity has been slow, but also by the belief that the convergence of emerging technologies and the increasing interest in manipulation will soon lead to a revolution in robotic dexterity. This panel will run for about 40 minutes, followed by questions from the audience. You can submit your questions at any time using Zoom's Q&A function. Now it's my pleasure to introduce our moderator, Oliver Kroemer. Oliver is an assistant professor at the Carnegie Mellon University Robotics Institute. He received his bachelor's and master's degree in engineering from Cambridge University. He then joined the Max Planck Institute for Intelligent Systems in Tübingen and received his PhD in machine learning for robot grasping and manipulation in 2014 from the Technical University of Darmstadt. After a postdoc at the University of Southern California, Oliver joined CMU in 2018 and is the head of the Intelligent Autonomous Manipulation Research Group. Oliver's research focuses on developing algorithms and representations to enable robots to learn robust and versatile manipulation skills over time, with applications in homes, restaurants, and hospitals. Oliver's research spans a wide range of robot learning methods, including reinforcement, imitation, and self-supervised learning. One of Oliver's core research interests is in interactive learning and having robots learn the structure of problems autonomously. The field of robot learning is growing at an incredible rate, both in terms of the development of new algorithms and in the availability of data for training. These developments have a major impact on robot manipulation and dexterity, providing new opportunities and changing the way that we approach problems. To explore these challenges and opportunities, Oliver has invited experts in robot learning to discuss the state of the art in learning for manipulation and what lies ahead for this field. I'll now pass it on to Oliver, who will say a little more about this exciting research area before introducing the panelists.
Thank you, Kevin. It's a great pleasure to serve as the moderator for this webinar on the grand challenges of robot dexterity. I also like to thank the audience for joining us today. For this session, we will be talking about robot learning for manipulation dexterity. In the future, we want robots to be capable of performing a wide range of tasks to support humans and improve their quality of life. These robots could be working at homes, hospitals, factories, farms, restaurants, or even parks. Many of the tasks in these domains involve interacting with objects, and hence manipulation is going to be a key capability for opening up new robot applications. A key challenge to working in these open world environments is the need to adapt to new objects and task scenarios. So manipulation tasks require robots to generalize between different objects, to consider multiple sensor modalities, to reason about object dynamics and switching contacts, and to think multiple steps in advance. So machine learning provides robots with this ability to adapt and handle these challenges based on data. And we're seeing more and more data available to robots. So there are many information sources that robots can use to learn manipulation, including human demonstrations, simulation, the internet, previous skills, and obviously the robot's own experiences. Such different information sources can be harnessed using suitable types of learning approaches. And one of the key challenges of robot manipulation is figuring out how to combine and balance between these different approaches to achieve data-efficient learning. To help us get a clear view of this important research area, I've invited 4 technical and thought leaders in the area of robot learning for manipulation to share their views on the state of the art and the challenges posed by robot manipulation. For this panel, I really want us to think about sort of 3 core questions, which are, what are the strengths and limitations of different types of learning approaches? What are the specific challenges that manipulation poses to robot learning? But also, what are the unique opportunities that manipulation provides for learning? Importantly, we want to get a sense of how robot learning will provide robots with the robust and versatile manipulation skills needed to operate in complex environments. During the second half of our discussion, we reserve time to take questions from you, the audience. We've already received some great questions during the sign-on, and the Q&A function will be open through Zoom, so feel free to continue entering your questions. Kevin's going to be monitoring those throughout the session and passing them along to me. All right, now I'd like to introduce the panelists. So first we have Rika Antonova. Rika is a postdoctoral scholar at Stanford University and a recipient of the NSF/CRA Computing Innovation Fellowship. Her research interests include mobile manipulation with deformable data-efficient simulation to reality transfer and Bayesian methods for active global exploration and reinforcement learning. Rika obtained her PhD from KTH and a research MS degree from the Robotics Institute at Carnegie Mellon University. Next, we have Chelsea Finn. Chelsea is an assistant professor in computer science and electrical engineering at Stanford University. She also spends time at Google. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. She received her bachelor's degrees in electrical engineering and computer science at MIT and her PhD in computer science at UC Berkeley. And I'd like to ask the panelists to all turn on their videos. Animesh is our next panelist is Animesh Garg. Animesh is a Stephen Fleming early career professor in computer science at Georgia Tech. He's on leave from the University of Toronto and Vector Institute. He is also a researcher at NVIDIA. He works on algorithmic foundations for generalizable autonomy, specifically on understanding structured inductive biases and causality for decision-making for manipulation. And finally, we have Andy Zeng. Andy is a senior research scientist at Google Brain, working on machine learning and robotics. He received his bachelor's in computer science and mathematics at UC Berkeley and his PhD in computer science at Princeton. He is interested in building algorithms that enable machines to intelligently interact with the world and improve themselves over time. All right, so thank you all for joining me here today. To begin with, I'd like to start with some opening questions. Let's see. Rika, can you tell us a little bit about your research and what you have been working on recently? Rika, you're muted.
All right. Okay. I was going to say I will accompany the explanation with some illustrations, but some sound will also be good. So yes, generally I work on Bayesian methods for active global exploration and reinforcement learning. And in terms of robotics, I kind of apply these to the problems of data efficient sim-to-real transfer, and also most recently mobile manipulation problems, especially for manipulating with deformable objects. So I'll just briefly summarize my previous work on using Bayesian methods for data efficient sim-to-real transfer. And that includes a line of work on simulation-informed kernels, where we collect a large amount of data from simulation, but then we learn transform that lets us connect how controller parameters actually influence the behaviors, and also embed the kind of like longer-term trajectories and behaviors into lower dimensional spaces so that we can adapt them online. And then my approach is to deploy a Bayesian optimization method with a neural network kernel that is utilizing that transform, so that we can actually run global search for optimal controllers on hardware, like, for example, learning to walk with this biped, and are able to do this directly from hardware with the simulation kind of providing the reshaping of this overall space. And so we have shown previously that this works on other domains other than locomotion, like, for example, task-oriented grasping, and also hexapod locomotion, and also some tasks in non-prehensile manipulation tasks. So most recently, I started being interested in working with mobile manipulators, and specifically considering what can we first do to bring simulation a bit closer to reality. For that, we can use differentiable simulators. Here's some quick examples of how that alignment would be done to infer the material properties. However, this is a pretty challenging problem. So, there are interesting research questions to consider there. We can also use non-differentiable simulators and then work on creating interesting representation learning techniques in order to capture the state of deformables. And so my current work is on applying these, previous very recent works on to the domain of mobile manipulators, where we manipulate either in assembly tasks or in everyday environments, or with large deformables such as blankets. And I'm going to be soon transitioning to a new role after being a postdoc. So I'm mostly also excited about new directions with new collaborations I've recently established, like, for example, how we can leverage actually novel types of hardware, like neuromorphic hardware, for global optimization with Bayesian methods. And also in terms of manipulation, how can we manipulate deformables, like, for example, this super challenging problem that NASA has of using Astro-B robots that are actually moving in 3D in space with the task of having to transform deformable cargo bags. So those are my research interests for now.
All right, great. And it's great to see such a wide range of different robots. Chelsea, you've worked on a lot of different sort of types of robot learning. How do you envision the future of robot learning?
Yeah, so I think that to me, one of the biggest bottlenecks and one of the biggest challenges in robot learning and in robotics as a whole is learning low-level motor skills, and that's also what I'm most excited about working on. And I think that when you think about motor skill learning, there's two different axes. One is the complexity or the dexterity of the skill, and the second is actually how well that skill is able to generalize to different environments and scenarios. And I think that we can think of a lot of kind of industrial automation as being somewhere on this plot where they can do somewhat complex things with very little generality. And what I'm really excited about is, can we enable robotic manipulation that's closer to, say, the level of a 5-year-old, or even better than that, such that we can do complex skills in many different environments and many different scenarios. To give a little bit of a concrete taste for what I mean by this, we've worked on a couple different recent projects that try to push the complexity and the generality of low-level motor skills. And then the first one, we are looking at building a teleoperation system that makes it very easy to teleoperate complex skills with a robot, such that we can collect data and then use that to train policies with imitation learning to perform dexterous manipulation skills, such as tearing off a piece of tape and putting it onto a box, slotting a battery into a remote control, putting on a shoe, and taking a lid off of a plastic cup. And so this is kind of pushing the boundary of the complexity of skills, of low-level motor skills that robots can learn. And on the generalization front, I think that this has actually been a lot more challenging in some ways. I think that in robot learning, typically the paradigm is that we first collect data for our project, we train a policy with robot learning to do some task with that data, and then we don't use that data again. We kind of repeat this process for each and every project, where we collect a new data set for the kind of purpose of that project. And this seems somewhat reasonable for robot learning, but if you instead contrast this with what machine learning research does, this is actually quite different. So in machine learning research, typically a large data set is collected once and it's reused many, many different times. And this, I think this paradigm is really important because it means that we can actually leverage a much larger and broader data set in order to generalize much more broadly. And even better than reusing a data set would be reusing a pre-trained model trained on that broad data set. So in the future, I think that it's really important for robot learning to move towards something that looks a lot more like what's on the right. And we've been doing a little bit of work along these lines, where we've been trying to think about, can we build data sets that are diverse and reusable? Can we develop pre-trained models that can be used for many different tasks and environments? And ultimately in the future, I think we need to be, as a community, moving towards data sets and models that can be reused, not just across tasks and environments, but also across institutions and across different robots as well. And I think that this will allow us to build robots that can perform low-level motor skills in a particularly generalizable way.
I love how you're thinking both about sort of the actual robot manipulation, but also as researchers, how we can kind of improve the process overall. That's fantastic. Animesh, so you work a lot on these ideas of generalization. Chelsea just mentioned kind of a very important axis. What do you think is the biggest roadblock in our current perspective?
Wonderful. Thanks a lot. I hope to provide at least some illustrations less about just main points of work, but more about what perspective I take. So the core question I'm trying to understand or have recently been very excited about is understanding reasoning and control, and very much like Chelsea, of how to achieve low-level skills for manipulation. Basically, a simple way of saying this is, how do we do everything that we do with our hands? What is the magic behind the magic sauce? And this is something that has stayed with me, where perhaps we learn how to do a task in some settings, and then we have a notion of generalization, which can be equated with cognition. And to answer this sort of technical problem, I believe the solution requires some notion of structure. So you can really think of structure as inductive biases, model architectures, and so on. The other side of the coin is indeed data. Where does the data actually come from? And finally, how does this loop into decisions? Decisions for reinforcement learning algorithms, decisions for planning in general, and how do we achieve the kind of, let's say, transfer efficiency in generalization and autonomy? Over the years, I have worked on many robots or many robot systems, which have ranged initially from pure manipulation, but over the years, this has now increasingly becoming mobile manipulation, even legged locomotion. But I think I'd like to hopefully explore more today is what leads to this generalizable autonomy in intelligent control for manipulation. If I start saying, is it nature or is it nurture? What leads to, let's say, the ecological pressures, and now framework-wise or algorithm-wise, is it more about figuring out where the data comes from? Is the data real or simulated, and so on? And these are the questions we work on actively on my research.
Very exciting. All right, and then Andy, so what have you been working on recently?
Yeah, so I work a lot on manipulation, getting robots to pick stuff up, maybe move them around, and I do this a lot with machine learning and vision. Some of my favorite projects in the past include TossingBot, learning to accurately throw a wide range of objects into target locations across the table. Transporter nets, which is learning to precisely pick and place objects without poses and doing it in a data efficient way that's practical for industry. And implicit BEC, behavior cloning, a new way to do BC, but also one of the first times when I became convinced that it was possible to learn the subtleties of pushing and intentionally making and breaking contact, reacting to different friction dynamics with high rate feedback from raw pixels. So when we started these projects, we just wanted the robots to do the thing well, and machine learning originally was just a means to an end. But over time, we also realized that there was this greater opportunity to explore the reverse, which is how robots can interact with the physical world as a way for our models to learn bottom-up common sense. So in other words, a data-driven prior for how the world works. Fun story, I was debugging TossingBot one day, and it turns out that if you visualize the latent features that the deep network had learned, it was effectively learning to group objects together based on their physical properties like shape and friction, because that influenced the throwing. And it was amazing to see how the whole concept of objects naturally emerged through the interaction without any labels. It was like small things like this that over time began to add up and eventually, I think, give credence to the idea that it may be possible to build general robot common sense with machine learning. But the challenge is scaling up. And so we spent a year trying to do just that, only to realize how much data we needed was exponential. But then 2 years ago, we also realized that we have a lot of internet data. So why not bootstrap some of this common sense off of the models that we've already trained from, books or engineering forums to meet us halfway, so to speak. So recently, my team and I have been exploring this in several ways. First is SayCan, and this uses large language models like GPT to generate a step-by-step plan and then use affordance functions to ground each of those steps to a pre-trained policy. Socratic models is this idea that when with language as middleware, we can get multimodal models like visual language models to talk to each other for some degree of reasoning. And this eventually gave rise to inner monologue, which improves the SayCan framework to use closed loop visual feedback for replanning. Palm E is our latest edition where we directly fine-tune one large multimodal language model for robot tasks. We weren't intentionally aiming for it, but we became state-of-the-art on visual question answering and is currently the largest deep network ever trained, which is kind of cool. Bootstrapping off of language for common sense does have its limits too. And I know there was a request to clarify the connection between large language models and control. So I thought I'd spend 2 minutes just to briefly talk about that. So far, we've had encouraging results on the high-level reasoning side for perception and planning, but how these foundation models can benefit control is still an open question. The challenge being that there's not a lot of paired language and control data for us to work off of. And so the question is that we've been thinking a lot about is, do we still have to rely on imitation or RL or engineered controllers? So last summer, Jackie, one of Oliver's students, joined us for an internship. And while we were tinkering with the models, we realized that code is effectively a linguistic representation of actions, be it calling primitives or invoking robot-specific control APIs at the level of torques, to some degree can all be expressed with code. And so it so happens that we have massive amounts of pre-training data for it. So our LLMs are quite capable of that. In fact, you can try it out for yourself. If you go to a playground like GPT's, you can go ahead and type in, if you see an orange, move backwards, and then type in if detect object orange robot.set velocity equals to -0.1, y equals 0, z equals 0. And so the point of this is to tell the language model an example of an instruction that we wanted to do, and then what an API would look like if it was expressed in code. And then we can say, move upwards until you see the apple, and have it try to complete it. So this is just a generic language model. It has code writing capabilities, but the way in which it expressed this functions, there's a lot of things going on here. One is that it swapped out orange with apple. It also switched this if statement to a while statement in order to respect the task. And it also assigned a canonical coordinate frame, so upwards means z. So this is an example that gives a hint at how data-driven common sense can be expressed through the parameters of a function from large-scale data of code writing models. And we effectively took this to the extreme, built various systems that can do various different tasks on different robots. And it harkens back to the classic work from Tomas at MIT on robot programming, using modularity as infinite use of finite means. But what this means is that instead of having an expert roboticist to program your robot, you can now have a language model do it for you. So just overall, I think that we can start poking at, for example, one thing that Jackie discovered is that you can get them to write PD controllers and impedance controllers as well, because they happen to have read your robotics textbooks too. And so if you request keep the pull upright with PD control, these and slot that into the generated code into an environment, it actually solves the task out of the box too. The caveat there is that we got lucky with these PD gains here. And so figuring out how the language model could tune the gains accordingly to visual feedback is still an open question. I'll stop here, but hope this helps a little bit with the context.
Thank you, Andy. I'm glad that you brought up the issue of data. So obviously there's lots of different kind of data sources that are available. I always like to think that, you know, the most important one, most valuable is maybe the human, as, you know, an expert in manipulation. And so, you know, one of the key challenges obviously has been in using human data is the discrepancy between the human and the robot's embodiment, also known as the correspondence problem. And so, Chelsea, you've done some work on sort of deliberation and visual demonstrations. To what extent have learning approaches addressed the correspondence problem or changed the form of the problem?
Certainly, yes. So I think that human videos are a pretty exciting form of data because there are a lot of them on the internet, and humans are really experts at manipulating objects. So it's a pretty exciting source of data. At the same time, there is this gap between the appearance of human hands and the appearance of robots, and also the physical capabilities of human hands and the physical capabilities of certain robot arms. So there's a pretty challenging gap to overcome. And there's actually been a pretty wide range of approaches that have tried to address this gap, some that try to address it fairly explicitly by kind of translating between human data and making it look like robot data and vice versa, and also much more implicit approaches that try to basically try to use the data and train models using the data without having to actually explicitly solve the problem. I think that the problem, I think, certainly still exists. I think that you can do a lot with more with robot data than you can with human data. And I think that at the end of the day, we'll probably want lots of robot data. But at the same time, we've certainly seen positive results where you can, for example, learn very powerful visual representations with videos of humans. And I also think that as we, possibly as we can start to use more powerful neural network models, we might be able to leverage them to learn more than just a visual representation, such as learning a dynamics model, or learning how to do, learning more about the world than just how to see.
Nice, yeah, good to build up some of that common sense in robotics. Yeah. So another very important source of information is simulation. So often, we provide robots with certain simulation environments for the tasks they have to explore. Rika, you've been doing a lot of research on using simulation for deformable objects. What do you see as the key challenges for employing simulations in new manipulation domains?
So I think one challenge is, closing that syntaxal gap. The issue might be that for fast simulators, for example, for deformables, the gap might not be closed at all, i.e. there is no setting for parameters such that the behavior of the real object would match the simulated one. And if we make the simulations more flexible, and there are, we know how to do simulations to really high fidelity, but then we are facing 10x to 100x to 1000x slowdown compared to real time. So that's a bit of a challenge in terms of seeing it as a sort of a fast source of data. But improvements in simulation and scaling that up could help. The other thing is that we can push in some novel directions. For example, differentiable simulation has been really, really promising, and people think that on that we can do a very quick progress with gradient descents and gradients being directly available. But we just have to be mindful of the fact that actually these optimization landscapes, even for deformables, are pretty rugged, and then can have various things where the gradients can get stuck, such as plateaus or deep local optima and local roughness. So I think this direction is promising, but we have to keep in mind that it's not straightforward. So, more research is needed.
Absolutely. And you mentioned improving simulations as well. So Animesh, you spent some time building new simulators at NVIDIA. What do you think are the challenges, and what should we expect from advances in this area?
I think, as Rika said, simulation, particularly of interesting phenomena such as deforming materials or maybe even fluids and soft objects, is indeed something very interesting and important. But I'd like to say that I think simulation, at least the way roboticists see simulation, is actually a combination of the triad of physics, assets, and let's say rendering. So often when we say simulation, it's not just the physics. Of course, all of the advances in graphics, solvers, numerical solvers is important. But I think for robotics, it's not just the solvers, but also large-scale assets, right? To create large-scale set of tasks, we need good assets. It doesn't matter how good the soft body solver is, or if it's a differentiable solver for that matter. That, I think, has not yet been automated. There's a lot of recent work in generative AI that is helping that process along. But being able to create good assets in a large set of environments is something that has been a bottleneck for a long time. That's one. I think another bottleneck is often just the definition of the task itself. When you look at any of these benchmarks that we use for reinforcement learning, often the task itself has been very carefully engineered by someone who has provided you with some underlying reward functions. Often many of those reward functions are not really available when you do something new, right? It's like, what is a reward function for cutting a lemon into 7 slices kind of thing. And now, of course, that's something for low level. And as you go to, let's say, larger or more complex procedural tasks, the same problem exists. And there's a lot of effort in the community to do this, but it still stays a problem. Now, as a community, we have also gone back to using human data via either direct capture or through teleoperation. And I think that is one final question that remains in front of us. Is human data sufficient? Or as Chelsea said, I think human data may never be complete in a sense. We might always need robot data or self-explored data. So in that sense, I think, just to recap, it's like we need to figure out how to specify tasks at scale procedurally. We need good assets that look like our kind of assets. And then finally, we need some mechanism, if we are going to use anything like LLMs, to provide supervisory data, whether it's algorithmic or people. That remains to be seen.
Great. Yeah, I mean, just thinking about sort of simulation and sort of the, you mentioned about sort of being able to create those assets. Obviously, there's always the question of sort of sim to real, but also real to sim. So Rika, what you've also been done a lot of work with simulations. What do you see as the role of representation in transferring knowledge between skills from sim to real?
Yeah, so I think one of the challenges there is, of course, for example, for real to sim, you can have some data that you are trying to transfer from, right? So then there is a question of like how telling the data is, right? And so I think what we are converging to as maybe a community is kind of putting it into the loop of real to sim, sim to real, real to sim, sim to real, and so on. So that's good. So then you have better and better data for doing your real to sim, because your policy now for interacting with these objects is somewhat, is doing something more interesting than just randomly shuffling them around. But I think also in terms of, we mentioned some, what representations we use and what representations we construct and how this relates to transfer learning. So I think it would be useful to build what I would call transferable representation. So in a way, instead of just training some deep neural net from scratch and then sitting down and solving the big and challenging, transfer learning problem of how to avoid catastrophic forgetting, how to figure out how to interpret this all, big blob that we've learned, I think we can focus on building modular representations from the get-go so that maybe they're even somewhat interpretable because of the modularity, and then kind of building on that, like adapting the pieces which have the largest part of the mismatch while not being bothered by the pieces that don't have a large mismatch. And I think that the curious part could be kind of in the current day and age, as Andy was kind of showing us previously, the power of these language models, like some of the interpretability might come from us being able to connect a little bit better to the language and to the what are we doing with objects in terms of kind of programs and so on. And some of them will remain kind of like a little bit further from that area and will be more about the dynamics and the interaction with the objects. Yeah.
Right. So in terms of transfer learning, so there's definitely the sim to real, but it's also obviously transferring from different other sources, so from real to real. Chelsea, how do you see the role of transfer learning for robots performing manipulation tasks in open world environments?
Yeah, so I'm excited about transfer learning for like a pretty different reason, which is that I think that ultimately, we've talked about the importance of data, and ultimately I think that we need data that's very diverse, and we can't hope to collect a lot of real data in an online manner. And so ultimately, I think that if we're able to reuse real robot data that was collected in other contexts, collected with other robot embodiments, collected with previous versions of the robot that we're working with, then I think we might be able to get a much broader data set and ultimately allow robots to generalize more broadly, possibly even in real unstructured environments. And so I'm really excited about whether we can basically do a form of pre-training on existing prior data sets and then transfer from that. And I think that we've seen lots of success of this in other areas of machine learning, like in natural language processing, computer vision, where you pre-train a really large model that is kind of a coarse generalist at a lot of different things, but isn't really, really good at any one thing. And then you can fine tune it for a very specific task that you want it to do. And it works pretty well with less data than if you were to train completely from scratch. So that's a really basic transfer learning recipe. I think that also there's more sophisticated ones that we can imagine as well. But really the key thing that I'm excited about in that space is reusing data, and which may require transfer across robots, across tasks, across environments, and so forth.
So there does seem to be kind of a bootstrapping challenge there of like, how do we sort of, like we want all this data from robots working in these complicated environments, but in order to get that, it'd be great if we had data to transfer from. So how do you kind of imagine that bootstrapping process? It's like, how do we get that, first lifetime of a robot of data? Or do we already have
I think there's lots of ways that we could imagine that bootstrapping happening. It could happen with simulated data, and I think there are people here that have thought about that. I think that part of it can also be an investment where we spend the time to collect a lot of data. But at the same time, there are also some existing data sets out there, and for every robot learning experiment, people have thrown away data, and so we could just try to patch together data like that. Another effort that I'm excited about that we're working on is trying to kind of bring together people from at this point, I think more than 10 different universities to actually come together and kind of spec out what we want in a data set, and each collect data at different universities. And I think that if we kind of distribute the effort towards this data set that I think a lot of people in the community want, then it'll be less work for every individual person. And hopefully at the end of the day, we'll have a data set that we might be able to bootstrap off of effectively.
That's great, yeah. All right, so I want to shift gears slightly from sort of data and sort of transfer learning and thinking about, well, maybe it's still connected to transfer, sort of large models and a lot of pre-training. So there's a lot of interest in sort of this idea of a foundational models. We see these often in vision language, where a model has been trained on vast amounts of data and can now be applied to various different learning applications. One that's sort of been, very much in the press recently is large language models. Think about how we have these sort of human, or natural language inputs. And Andy, I'm wondering, from your experience, what information do LLMs provide for robot manipulation that previous information sources have been missing?
Yeah, so one thing that has struck me as particularly challenging from other data sources is this notion of behavioral common sense and enabling our robots to express or react to that respectively. So one example is, say that a person was just asking a robot to change its trajectory according to a spatial command, move a little bit to the left. It's subtle, but it's like, in order to capture that in the trajectory itself, what does a little bit to the left mean requires a lot of contextual reasoning that needs to be baked in, and a lot of priors and expectations for how that should actually directly translate to a difference or a delta in the control. So things like that. Other examples are push harder or go faster, that's temporal, or maybe even functional, like self-balancing. These are all different nuanced ways in which I think behavioral common sense, in my opinion, is like the dark matter of control. We know that it exists, but it's very hard to pin down, and we don't know quite how to capture that. So I think at least with LLMs, it feels like there's some capacity to be able to from potentially books, for example, capturing a little bit of that information at that expectation and prior, and bringing that over into some of our controls. So for example, that sort of extends beyond control as well into processing this sort of more fine-grained sensory experiences that a robot might have. So for example, if you had a large language model that was trained on books, it's very likely building this representation of how sensations map to experiences. So for example, say that there was a book and there was a snippet of text. As you stand under the scorching sun high up, you feel the bumps of the pebbles beneath your feet. A dry and sandy gust of wind brushes against your face. The heat presses against your chest. As you feel a single drop of sweat roll down the side of your cheek, something like that. The statistical cohesion of those words occurring next to each other, they help to describe an expectation for what the experience of being in a desert might feel like. And so if your robot was going to be experiencing that, as long as you have some way in which you can map the words to the percepts, you have some way in which you can capture that prior. So I think there's a degree in which we can find some way in which we can bridge that link. And I think that finding interesting ways to bridge that link, maybe from unlikely data sources like code, I think would be very exciting to explore.
Great, yeah, no, it's great to think about that kind of embodiment. Kind of building on that, Animesh, seeing that there's been a lot of work on sort of, foundation models, computer vision, and language, what do you see as sort of other challenges to sort of bring these to robotics?
I think this has been said. The problem is foundation models are trained on data that is, let's say, widely available. And then, as Andy said, it's what we are really after is this sort of behavioral common sense gray matter. It turns out that what we really want our robots to do, I think Chelsea said this, is like low-level skills. Nobody talks about this. We don't describe how we open the door or we open because this is something that, like, if you and I meet, you're not going to tell me how to handle my cup of coffee. That's like, we just assume that's common prior motor knowledge. So I think one way to describe what is really missing is we need to make decisions at different levels of temporal scaling. Let's say you can think of this as skills and tasks or procedures. So skills is, let's say, what you would call motor level intelligence, and tasks and procedure is what you would say cognitive intelligence. And there is also a lot of, let's say, neuroscience evidence which says there are different things that we learn from imitation versus different things that we learn from what you would call self-practice. Right? 0 to 7 years, you do a lot of self-practice, and then a lot of learning after that is very quick because you're learning from imitation. Like you learn how to use keyboards by watching others, but you learn how to actually move your fingers yourself, kind of thing. So I think the part that is really missing is we don't know, first of all, how to specify the objectives of low-level skills. 2, if we were to say, ask this question, what is a foundation model for low-level skills? It's not clear if it's all one per skill, if it's per skill, or if it's like the singular model, is it specific to every agent, and what would be the objective for something like that? And I think the real question here should be, and it's not just like that the foundation models will only be separated by the temporal horizon. Sometimes foundation models can actually enable new modes of exploration at the low level. This is something we see in sports, for example. Like, a whole generation of people is doing long jump like this, and then one person figures out, and then everybody moves over to the new style. It's a low-level motor control, but exploration was very hard. So I think the part that is really missing is the grounding that gets us the low-level common sense. Once we have that, then we can assume that we can have, let's say, 2 kinds of foundation models. One is agent-specific, which tells you how to do things, and then one is, let's say, cognitive, which is telling you what to do. And the what model could be completely agent independent.
Great. Yeah, no, so it's definitely a lot of nuances to going for more robotics. And yeah. So we're going to switch over now to some of the Q&As from the audience. So I'm going to start off with one. So is previous research on physics-based planning and control for robot manipulation useful in your work? If so, how? If not, why not? Who wants to talk about physics in their work?
I can say a few words before everybody else jumps in. So first of all, of course, simulation, since I work with simulation, right? All of the things that we discover about how to model things, they come directly from physical knowledge, from, like just foundations of ion mechanics or, fluid dynamics and all that stuff, right? The other thing, the curious thing on a slightly higher level, like there was a bit of a question about control. So for example, when we were optimizing gates for a bipedal robot, for the search space, we didn't try to search over the structured space. We actually tried to search over the space of the gains or the parameters of the controller. That controller was closed loop, and it actually was kind of like we've experimented with a few different kinds of, so to speak, traditional controllers for bipedal locomotion and some novel like neuromuscular controllers for bipedal locomotion. So all of that knowledge built in, including the sim and the dynamics of the robot, including the controller structure, that was all useful. And on top of it was learning and exploration and all that stuff. So I think, fundamentally, the reason why we need all of these things is like the structured kind of space and exploration really allows us to get the ultra data efficiency that we need for experimenting with real hardware.
I guess to add to that, so we certainly use kind of physics and control, or we build on that knowledge in a number of ways in our research. For example, we do use simulators all the time for prototyping, for example. Maybe to make a slightly more controversial point, we've also had scenarios where we don't use it at all. And we, in the work that I presented on learning complex manipulation skills, we weren't actually even using forward and inverse kinematics whatsoever. And we actually found it beneficial to not use forward and inverse kinematics. We were doing control directly in the joint space, and we found that if we did it in end effector space, you would run into singularities, especially because those low-cost robots don't have any redundancy. And when you want to do very fine manipulation skills, you might be hitting kind of coming near those singularities, coming near joint limits and so forth. And it was smoother to operate directly in joint space. So while there have certainly been scenarios where kinematics and physics have been useful, there have also been scenarios where it's actually been beneficial to throw it away. And I don't have too many qualms with throwing away if it leads it to work better.
All right.
Just to add to that, on the object sets part, or in terms of operating on tasks where mostly working with rigid objects. For example, tossing bot we were putting in some of the physics equations directly inside of the model architecture, and that prior ended up helping with data efficiency. So there are instances where under the right conditions, including some prior physics knowledge could help. I think where also just potentially a controversial point, which is once we start touching more deformable objects or things where the dynamics are much more unpredictable, that's where these things start to fall apart. And I think that it has been, in our case, at least helpful just to directly learn end-to-end, for example, on deformable tasks to be able to react to those unsuspecting dynamics.
I'm glad that you brought up the tosspot, actually, because the next question from the audience kind of reminded me of what you were telling earlier about the tosspot. So the question is it important that AI be explainable? What are the methodologies for validation, verification, or assessing reliability?
Well, yeah, I think in terms of being able to, so there were a couple papers in the HCI community that was discussing if we were going to have robots or machines that are constantly interacting with people every day, what are the things that you need in order to build trust between the machines and the people? So there were two things that contributed. One is, did the robot do the thing? If it was not reliable, then it was not trustworthy. But the other thing too was, could it explain its decisions? How much of it could it explain for why it did something? And that over time also builds trust. So I think that if we were going to imagine a world where robots are around us every day, that becomes quite important. And at least being able to communicate what it's doing in a way that is digestible by the people around him also suggests a little bit of contextual reasoning as well that would need to enable that. And so I do think that it's quite important to consistently be thinking about that when we build these systems.
I'm going to add that it's also very, it can be crucial for adoption. So it's not like people are more or less trusting for the robot, but it can actually take it from everybody, you know, it just doesn't take off. The technology just doesn't get into the society, and that's it. Like, the society doesn't get familiar with it. While if the technology gets little by little into the society, more and more people become familiar with it. And actually, you know, we humans, we learn very well, right? So like, we actually adapt to robots being around and kind of change our routines just a little bit to accommodate, and that builds comfort and so on. So I think it can be actually quite crucial for these sort of transitional effects, where if at least you start being able to get this technology in, then you have a hope.
Right. Yeah, that adoption is very important. And, you know, as roboticists, we always think like, oh yeah, people want robots, but yeah, that's not always going to be the case. All right. Another question from the audience. Or Animesh, did you want to?
Sure. Yeah, I think I do want to add that while we always think of explainability from the perspective of users, I would argue that explainability is necessary for future development. I like the use of simpler analogy like cars, right? I would argue the cars these days are fairly complex that most of us don't actually understand the relationship between pushing the pedal and the car going forward. That's the user sort of input output. It's reliable, but most of us don't understand this. But to improve the cars, there are some set of people who do understand the mechanics of it, every component, so that they can improve it incrementally. But as we do complex systems engineering, AI is not going to be very different, maybe slightly more complex. At least some subset of people need to understand why what is happening so that we can incrementally improve it. Of course, some people can argue that, oh, once we have all the data, these systems are going to be like a self-improving flywheel kind of thing. And I think that is true to only an extent. We will need to intervene in future iterations of whatever these models are going to be like. And unless we understand this, we will essentially be hitting limits, or we might actually be throwing too much compute and resources for problems that could have been solved much more efficiently.
Yeah. So obviously, you know, thinking about adaptation of technology, price is often an important factor. One question from the audience was, what are affordable ways to have machine learning for robot manipulation without super costly servers?
Simulators, GPU-based simulators.
Chelsea, I saw a bit of a head roll.
I mean,
What
I
are your
think that,
thoughts?
yeah, I mean, I think that basically machine learning has been relying on more expensive servers, specifically in scenarios when you want to scale to large data sets. And I think that there are some things that can be studied in small data regimes, especially if you don't care about generalization as much, if you really want it to do a fairly specialized task. And I guess the first work that I mentioned was all done on a workstation. It was learning like the tape task, for example, that was all trained on a workstation in a few hours. The workstation did have a GPU in it, so it wasn't like super cheap, but there's very, very little generalization of that complex skill. So there are some things you can study without super complex servers, but usually at the cost of being able to leverage broad data sets and generalize well. I guess the other thing that I'll mention is that I think that as we start to get better and better pre-trained models, that should also make learning cheaper as well. So if we can do something, if we can basically have a pre-trained model such that someone can download it off the shelf and run it themselves and maybe train something on top of that, that should also make learning much cheaper and not require as much compute.
So another question, how important is new hardware? For example, better actuators, better tactile sensors, faster, stronger, higher degree of freedom and effectors versus better learning. So it's very much a software versus hardware kind of question. Yeah. So do we want, what's better for new hardware?
Right. I think the interesting part here that we're coming to for robotics is it's very obvious that hardware is important, and for a learning person it's obvious that the learning algorithm is very important, right? But actually it's the sort of combination and what we call these days co-design of the two that is important. So we've explored previously co-design for morphologies and like what kinds of hands do you want, what kind of space can they span in terms of how you actuate them. But it's also, as the question asked, what about sensors, right? What kind of sensing is actually needed, but not only to execute the task, but also to learn the task. And these two might not be the same, right? So I think one of the things that we haven't really looked very closely at in the community is what sensing and actuation and hardware like morphology is necessary and sufficient for learning. And I think one of the things that kind of iterating on this co-design of the sensing as well, and what types of learning methods are kind of eating the sensor data and actually benefiting from it, that I think can open new doors out there. And I just wanted to emphasize sort of the difference for the needs. So for example, I give this example of turning clothes inside out usually. When you learn how to manipulate with clothes, you look at it, you figure out how does an edge of a clothing item feels, what does it mean to turn something inside out, right? right? But when you actually manipulate it, you're using all your tactile information. So it might be a different or a combination of modalities that you need to use during learning, while during execution, it might actually be sufficient to use only a subset of that.
I think one thing to add here could be that we definitely need better building blocks in terms of hardware. For example, better motors or better tactile sensors, or let's say better materials for hand effectors itself. But what is not clear right now is what is a good robot, or what is a sufficient robot in that sense, which is the combination of these things. Because often when we build these systems, we have a set of tasks in mind, and whether we like it or not, things are overfit to that particular setup. We are very good at automation in a sense as a community. So I think this question of like it's either or algorithms versus hardware, I don't think it's versus. It's more like algorithms need to continue to develop with the hardware that we have, in the assumption that we need to solve a large and a broad set of tasks that are not overfit to a particular, let's say. You can always make the task easy by over adapting the hardware. And I think that's not the goal of let's say, roboticists as a community.
Right, and ideally, we also have learning methods that can kind of span across different kinds of embodiments. That'd be great, yeah. So unfortunately, that brings us to the end of our Q&A. I'd really like to thank Rika, Chelsea, Animesh, and Andy for this fantastic discussion. Thank you for all your insights. Also, I'd like to thank the audience for joining us. We should appreciate if you would provide feedback on today's panel by filling out the survey that we will send to you. Thank you all again, and I'm now going to hand over to Kevin to wrap up the session.
All right, thanks, Oliver. And thanks, Rika, Chelsea, Animesh, and Andy for sharing your perspectives on how machine learning has impacted the study of robotic manipulation and the many challenges that remain ahead of us. This brings us to the end of our 5-part webinar series on the grand challenge of robotic dexterity. In this series, we've heard perspectives from companies innovating in robotic manipulation, such as Google, NVIDIA, Ambi, Berkshire Grey, Boston Dynamics, Universal Robots, Meta, and the Toyota Research Institute. And from leading researchers like we have here today, from universities such as Columbia, MIT, UC Santa Barbara, UC Berkeley, Stanford, Carnegie Mellon, NYU, Georgia Tech, the University of Toronto, and Northwestern. We've covered topics such as novel materials for end effectors, machine learning for manipulation, current and future industrial applications, and the economic and societal impacts of robots capable of translating advances in artificial intelligence to useful physical work. And you can find recordings of all the webinars on our website, robotics.northwestern.edu/grand-challenges. Even though we've covered a lot of ground, this is only the beginning of the conversation. I encourage you to respond to the survey that you'll receive shortly, and we'll look for ways to continue to engage on the topic of robot dexterity as it's poised to revolutionize our interaction with robots and the future of work. Thank you again to all of our panelists today, and thank you to you, the audience, for joining in the conversation.